Let's talk about the standard library containers. Vector and lists are examples of sequential containers, and you have observed that the interfaces are similar. Now, the C++ standard uses the term container to represent a class that can contain objects. C++ defines a common interface for all containers and then splits the set of containers into sequential containers and associative containers. And common requirements unique to these subsets are also defined, and individual containers have their own additional requirements. So here is a concept hierarchy that kind of shows that we have these two kinds of containers, and then here are the examples of the classes that are examples of those kinds of containers. And all of these classes represent data structures that we're going to talk about this semester. So this isn't an inheritance hierarchy. The term concept is used because it represents the set of common requirements for the container, sequence, or associative container. So a list and a vector may have several member functions in common, but they may not be used polymorphically. So there isn't a sequence class that these inherit from. That's why there's this word concept here to just remind us that, conceptually these are related, but they're not related through an inheritance hierarchy. So both vectors and lists, as well as other sequences, can be used interchangeably by generic algorithms. So the basic difference between a sequence and an associative container is that the items in a sequence have some linear arrangement, and for any given time, each element has a particular position relative to other elements. Now, in an associative container, there's no particular position for each item in the container, and the items are accessed by value rather than their position. So here are some common features of containers. Here are some type defs, some constructors, some functions, and a description of their meaning. So for example, here's a default constructor and here's a copy constructor. Here are a bunch of the comparison operators being overloaded. We've got the assignment operator and a destructor, the swap method to exchange the contents of two containers. We've got we can get iterators to point to the beginning or past the end of a container, the size of a container, and a Boolean function of whether it's empty or not. Now for sequences, here's a constructor. It constructs the container of type X containing num copies of some initial value. Here's a constructor that constructs the container of type X, and it'll have a copy of the items starting with the object referenced by this start iterator up to but not including the stop iterator. So two constructors, and here's an iterator and an erase method that take an iterator as a parameter, and then they return an iterator as the result. Here's some optional requirements for sequences, and you can look through here and see the different functions and a description of their purpose. And then here are some of the data structures that use this function. And you've seen vectors, and we're going to talk about lists now, and here are some other functions we'll talk about later in the semester. So you can pause and look this over more carefully on your own. Now you may wonder why the standard doesn't require all of these functions for all sequences, and the authors of the standard library chose to require only the functions that could be implemented in constant time or could be amortized constant time. So thus, pushback is required for all sequences, but push front is not required for a vector because push front is an order n operation. And the subscripting operator is not required for a list because it would have to traverse the list starting at the beginning. So it's an order n operation. Now the associative containers, they're designed for fast retrieval of data based on a unique value stored in each item called its keys. Here are the 4 associative containers we'll talk about in our book. And set and multiset only store keys, map and multimap associate a key with a value. And we'll talk about these associative containers when we get to chapter 9. Now the author's vector class back in section 4.3, doesn't meet the requirements for a sequential container. The insert and the erase functions were defined in terms of an index rather than an iterator. And we also didn't implement the begin and end functions. So it would be easy to modify our class so that it did meet these requirements. And the simple approach to defining the iterator and const iterator for the vector is to define them to be equivalent to pointers. So here's a type def that we can use to create an alias. So an iterator is a type that corresponds to a pointer to an item type. And a const iterator is a type that's equivalent to a const item type. Kind of a const pointer to an item type. The vector functions begin and end are then implemented as follows. So here's our begin function that returns a pointer to the data, and end returns the data plus num items. And since iterator is a pointer to this item type, that's the return type of these of this body. Now the vector contents are stored in array the data, so that the data is the address of the first element of the array, and the data plus num items is the address just past the last element. And this is the approach taken in many implementations of the standard. It's legal. A better approach would be to define an iterator class that held a pointer to an item and then a pointer to the parent vector. And the operators star, the dereference, and the member access operators could then validate the pointers before dereferencing them. Now, since this is a random access iterator, the addition and subtraction operations also must be defined. So the following function uses the iterator, and it's this parameter named POS rather than an index. So here's, we insert at the position indicated by this iterator, and here's the value that we insert. And here's the code to do that. We check that the position isn't out of range. We make sure we have space in our array, and here's where we do the insert operation. So we set the iterator to the end, and as long as p is greater than position, we decrement p minus minus, and here we have star p equals star p minus 1. So here we start at the end and we back up the specified number of locations, and then here we can update whatever this pointer is pointing to. We update the value and we increment the number of items. I guess, what is this for loop doing? What this for loop is doing, since we're going to increase an operator, we're taking everything. We have this point past the end of it, and then we're taking everything in the array and we're shifting it down one. We're taking something at position p minus 1 and moving it to position p. So here's where everything that's beyond where we want to insert, we're going to go ahead and move them one location in the array so that we can open up space. So when we get to this location, star pos is pointing to an empty location. So this code is equivalent to the version previously if we substitute the call to begin plus index for position and end minus begin for the number of items. And that's the end of this slidecast.